In the name of Almighty God, I am Master Sankoshi, and today I want to talk about chemical reaction engineering in quantum multiphysics simulation software. Now I want to go through the Stefan velocity. Heterogeneous reactions on fluid solid surfaces can affect the mass, momentum, and energy balances at the interface separating the fluid and the solid. On the reacting surface, the production or destruction rate (RSI) based on the SI is molar per square meter second of a fluid phase species is balanced by the total mass flux of the species. The mass balance for a species I and a boundary representing a fluid solid interface is given by the blue formulation. Here, n is the unit normal pointing out of the fluid domain. U is the mass average velocity of the fluid mixture based on the SI is meter per second. GI denotes the mass flux of a species I relative to the mixture, typically due to diffusion, and MI is the species molar mass based on the SI is kilogram per molar, summing the mass balances at the surface over all species results in an effective mixture velocity as follow, referred to as the Stefan velocity, here denoted US. To reach equation 3-207, the fact that the sum of all mass fraction is 1 and that the sum of all relative diffusive flux is 0 was used. Equation 3-207 implies that the surface reaction results in a net flux between the surface and the domain. A net flux in turn corresponds to an effective convective velocity at the domain boundary, and the Stefan velocity, it should be noted here that when solving for mass transport inside the fluid domain, an outer boundary of the domain corresponds to a position just outside of the actual physical wall on the fluid side. The domain boundary doesn't coincide with the physical wall. In most reacting fluid models, the species mass fractions in the fluid domain are solved for without including the surface concentration mole per area on exterior walls. The one reason for this is that the surface reaction rates are often not known. In this case, surface reactions can be modeled either by applying a mass flux or prescribing the mass fraction, or a combination of both. On fluid boundaries adjacent to the reacting surface, the Stefan velocity on a fluid domain boundary is then defined as the net mass flux resulting from the boundary conditions applied as follow. Here, the first term contains contributions from boundary conditions prescribing the mass flux, while the second contains contributions from the boundary conditions prescribing the mass fractions. Contribution to the Stefan velocity can be added by the selecting accounting for Stefan velocity in the flux or mass fraction features in the transport of concentrated species interface. The resulting Stefan velocity based on mass transport boundary condition is computed as follow. Using a reacting fluid interface, the Stefan velocity defined in the manner of equation 3-209 is automatically computed and applied on boundaries corresponding to walls in the couped fluid interface. The Stefan velocity is prescribed in the wall normal direction on the wall selection. Now I want to go through the chemical reaction rate for laminar fluid, or when the turbulent reaction model is set to none in a reaction feature. In the transfer of concentrated species, the default automatic reaction rate used by the reaction feature is based on the mass section law. Consider a general reaction belonging to a set of J reactions and involving I species such as follow. For such a reaction set, the reaction rates are J based on the unit molar per cubic meter second can be described by the mass section law, such as this equation here: chi j to the power of f and chi j to the power of r denotes the forward and reverse rate constant respectively. The concentration of species I is denoted is ci based on the is molar per cubic meter. The stoichiometric coefficient are denoted bij and are defined to be negative for reactants and positive for products. In practice, a reaction seldom involves more than two species colliding in a reacting step, which means that a kinetic expression is usually of order 2 or less with respect to the involved concentration. In addition to the concentration dependence, the temperature dependence can be included by using the predefined Arrhenius expression for the rate constant, such as follow. Here, R denotes the frequency factor and the temperature exponent. E, the activation energy based on the sun is joule per molar, and Reg, the gas constant. which is the value is 8.314 joule per molar Kelvin. The pre-exponential factor, including the factor frequency factor of and the temperature factor T to the power of n, is given the unit cubic meter per molar to the power of alpha minus n 1 per second, where alpha is the order of the reaction with respect to the concentration. Now I want to go to the non-isothermal reacting fluid. When a chemistry interface and a heat transfer interface are used in the non-isothermal reacting fluid multiphysics coupling, the heat equation is modified to account for reactions and diffusion. In presence of chemical reactions, the enthalpy based on the SI unit joule per kilogram is a function of temperature, pressure, and mixture composition. For a mixture of n components, the mass fractions verify the condition omega I plus omega I2 until omega n is equal to 1. Therefore, the enthalpy is a function of a temperature, pressure, and only n minus 1 mass fraction, such as follow. Assuming the same velocity for the convection term of all components, the mass fractions follow the equation as follow. On the other hand, using the chain rule, the enthalpy variation is written as follow, which can be written using the particle molar enthalpies as follow. Additionally, the heat balance equation in terms of internal energy is written as follow, where QAVD is the heat source from viscous dissipation and Q represents additional sources. The heat flux Q consists in a term of conduction and a term of diffusion. Enthalpy and internal energy are linked to the formula E is equal to enthalpy minus pressure divided by density or rho. We can thus rewrite the heat balance equation in terms of enthalpy as follow, introducing the heat capacity at constant pressure CAP based on the sign is joule per kilogram cubic meter and the coefficient of thermal expansion alpha P based on the sign is 1 per Kelvin, gives the following formulation. The term with the pressure derivative is a work of pressure forces QAP. The enthalpy variation due to the gradient of a species mass flux can be partially simplified with the diffusion part of the heat flux. The heat source of reaction can be written in terms of enthalpies of reaction HI instead of particle or partial enthalpies based on the reference one. The temperature derivative term can be expanded to make the convective term appear. We finally obtain the temperature equation for a free fluid with n species and m reactions as follow. For reacting fluids moving through the interstices of a porous medium, the heat sources of reaction and diffusion are only accounted for the temperature of the fluid phase, while the porosity is already accounted for in diffusion term through the mass flux. The heat source of reaction has to be multiplied by the viscosity and porosity. Also, in presence of a porous catalyst, both reactions in the bulk and reactions at the surface at their accounted are accounted for and in the reaction source term, where the epsilon p is the porosity of the medium based on the SI is 1, S area is the specific surface area based on the SI is 1 per meter, or the I to the power of S is the surface reaction rate based on the SI is molar per square meter second. An additional source term is added to model convective heat transfer between the fluid and the porous matrix to get the temperature equation for non-isothermal reacting fluids in a porous media. Now I want to go through the porous medium type. This equation is the one that is solved when the porous medium type of the porous medium feature is set to local thermal non-equilibrium, since both fluid and porous matrix temperatures are solved separately. With the local thermal equilibrium approach, the equation is written for the common temperature and in terms of effective material properties for the time derivative term and conduction term. I read literature that the references for the reactant fluid interface was written by Jacobsen, and the name is Chemical Reaction Modeling Multiphase Reactive Fluids in a Springer magazine, and was written in the 2008. Thank you so much for watching my tutorial video until the end. Today is 20th of May 2026. Time is 12:02 p.m. Also, you can download the proper and appropriate related computer multiphysics simulation software file from my github.com/masterscript.